Adrian got his bachelor's degree in electrical engineering from the Australian Defence Force Academy, then served several years in the Royal Australian Navy, got a master's degree in computer science, then worked as a software engineer in a variety of roles before getting a PhD from the Australian Centre for Astrobiology, I believe in planetary science.
That's right.
And today Adrian will discuss CRISM observations of Martian polar caps.
Thanks, Josh, and thanks everyone for coming along and showing an interest in this topic. I'll try to keep the diversions minimal, but I will start off with a little bit of a diversion. 2 weeks ago, the first landing of A319 passenger aircraft at Wilkins Runway in Casey Station in Antarctica took place. This is an Australian station, Casey Station. It's 4 kilometres long and cost the Australian taxpayers $49 million, most of which they're not going to be able to experience because it's not open to tourists, but it is open to researchers. So this is something for future missions to Antarctica to consider. Casey is one of 3 permanently manned stations in the Australian Antarctic claim. Here it is here. And there is also the Casey, Davis and Mawson here are the 3 permanently manned Australian Antarctic bases. And Mawson gives me a chance to talk about Sir Douglas Mawson and my connection, my tenuous connection to him. Mawson first went to Antarctica with Shackleton in 1907 and was in the party to reach the South Magnetic Pole. And with his mentor, another Australian geologist, Edgeworth David, was the first to climb, was in the party that was the first to climb Mount Erebus. He declined the invitation of Robert Falcon Scott to join his 1910 ill-fated expedition, Terra Nova expedition, in which Scott made it to the pole second, but perished on his return. Instead, Mawson led an Australian Antarctic expedition in 1911, in which he was involved in a sled expedition with 2 other members of the party, one of whom fell down a crevasse, taking most of the supplies, and leaving the 2 others stranded a month out from base with 10 days of supplies and 300 miles away from base. Obviously a pretty tenuous situation. They started their return immediately, but unfortunately with such low supplies they had to eat their sled dogs on the way. And after 2 months of this, the other member, Xavier Mertz, died of vitamin A poisoning from the dog's livers. Mawson himself made it back to base 4 months after the journey began, and 3 months after the first crevasse incident. So this was what is termed the heroic age of Antarctic expeditions, and obviously today, hopefully things have run a little bit more safely. My tenuous connection to Douglas Mawson is that he was head of the geology department at the University of South Australia, and he hired on my supervisor's supervisor, Martin Glassner. And Martin Glassner supervised Malcolm Walter's PhD, if any of you know Malcolm, who was head of the Australian Centre for Astrobiology. So that little diversion leads us to think about planetary poles, and these 3 examples from the Saturnian system show us that planetary poles are pretty damn special. We have the poles of the South Pole of Enceladus, which is spewing water out here, and lakes in the North Pole of Titan, and hexagonal storms in the North Pole of Saturn. Poles do pretty weird and wonderful things. Today we're not interested in the Saturnian system, unfortunately for many of you, but we're going to look at Mars. It also has poles, as was discovered by Jean Cassini in 1666, only 50 years after Galileo invented the telescope. Cassini had turned it to Mars and had worked out the period of its day, and also observed polar caps. About 100 years later, William Herschel used his telescope to interpret the polar caps as made of ice and used them to discover the inclination of Mars in his 1784 paper, The Philosophical Transactions of the Royal Society. So we knew a little bit about Mars's poles going into the period of spacecraft. And let's just let that play. Mars has an eccentric orbit so that it spends most of its time, or it spends the disproportionate time closer to the sun in one winter and one summer. So what we have here is a Mars that is tilted over at 24 degrees here. The North Pole cap here is pointed away from the sun when Mars is closest to the sun. And so Mars moves through this period of its orbit, following Kepler's laws, much more quickly than it moves through this period of its orbit. So it has an asymmetric winter and summer in both hemispheres. Essentially what this means is that the northern hemisphere summers are long, but not as intense. It's about 180 days long. And the southern hemisphere summers are short, about 140 days long, but very intense. And we can see that here on this. I think I've covered most of that. So after Mariner 4, one of the earliest models for what was actually happening in the seasonal caps of Mars was postulated by Layton and Murray in their 1966 paper, where they suggested that the polar caps were actually made of CO2 ice. Up till then, it had sort of been debated whether they were water or CO2 ice. And in fact, inferring from the telescopic spectroscopic information showing that the tenuous atmosphere of Mars was CO2, they predicted a model, or they put forward a model where the CO2 caps, or the seasonal caps, were made of CO2 ice. They were subsequently proven mostly right by Mariner 9 and Viking observations. Then after following a period of looking at Mariner 9 and Viking data, and where there were some excellent papers that I haven't mentioned there, including one by Jeff Briggs in 1974, looking at the polar caps. Kiefer in 1976 used Viking infrared thermal information to look at the temperatures of the ice caps, knowing that the ice caps, if they were water ice or CO2 ice, should condense at different temperatures. He inferred that actually the north cap, the north residual cap, that we'll see in a second, is water ice, and that the south cap was CO2 ice, or that the south retained a CO2 ice cap throughout the summer as well. We'll just have a look at those residual caps here. So what Viking left us with, and I'm playing a game here, you can't actually see Mars at any time in this configuration, as you'll no doubt realize. This is the residual cap, so it's summer in both hemispheres here. On my left, or on our left, is the north cap, on our right is the south cap. So the important point to take away is that these residual caps are water ice in the north and CO2, at least CO2 retained on top of the residual cap in the south. Mariner 9 and Viking also picked up polar layer deposits lying underneath the residual caps. And you can see the layering here. These have been used to try and infer a history of what's been happening globally on Mars, because the layers are thought to form when a relatively large amount of dust gets into the atmosphere and falls out on the polar caps. However, some of the mock scientists have actually taken images like these Mars Observer camera or Mars orbiting camera, and the polar layers they interpret as stratigraphic layers. There is a little bit of debate as to how the polar layers have actually formed. Mars Global Surveyor has turned back a huge amount of data of the poles, including this one here showing the North Pole seasonal cap extending out to about 70, 75 degrees here. So this is in springtime or fall, but it's in springtime in the north. We've also got data from the Mars orbiting laser altimeter that has shown us the variation in snowpack heights as a function of seasons. So you have here in the northern winter, building up of snowpack ice up to about 1.2, 1.5 metres in the northern winter. The springtime decreasing amounts, and then in summer minimal amounts. Same sort of thing happening in the southern hemisphere, but a lesser amount of ice being deposited. And remember, that's mostly because of the shorter southern longer polar winters and shorter summers. And also this demonstrates the effect that dust storms can have on the polar caps and interrupting their condensation during the fall period. So this is a Mars Orbiter camera image of the South Polar Cap at about L sub S 211. I'll talk about what L sub S is later on. And you can immediately pick up that the cap is not, the albedo of the cap is not uniform. And in fact, we have this dark kidney-shaped region here, which is of interest. This is the residual cap here that I showed you before in the Viking images. And the seasonal cap is extending out here, out to about 70 degrees south here. There's cryptic region here, and it's showing up in the molar data here at 1 micron, is actually of interest because of also some of the features that are found, including these Swiss cheese type features, which appear to be circular, semicircular depressions in the ice cap. And what we think here is happening is that there is a thin CO2 cap in the south, that's this region here, covering over a water cap here, so a very thin layer just over the top that's subliming away. And in fact, it has been mapped as disappearing in some areas, but it's also been mapped as growing in some areas. So it's a bit of an open question as to whether the CO2 residual cap, or the CO2 frost on top of the residual cap is actually stable or growing or shrinking at this time. We also have these strange features here, which during quiescent times look like cracks that people have described as spiders or spider-like, arachnoid or arachnid-like. And when these have been imaged by in this case, HiRISE on Mars Reconnaissance Orbiter, we see these features blowing away in a particular direction or moving away from these cracks in a particular direction, which has led people to think that they've been controlled by the wind. And you see in this closer in part that they actually have, they all seem to emanate from a point and blow in a direction that covers, in this case, about 50, 60 degrees of area. So it's local winds that are thought to be controlling the deposition of these black regions, and we just close in on those. And what's thought to be happening, and a lot of this work has been done by Hugh Kiefer and Tim Titus at USGS, what's thought to be happening by them is that as the sun rises over the polar regions, it shines straight through a CO2 translucent slabs and heats the ground beneath that slab. So you have a heating of the soil beneath the slab, which builds up the pressure beneath it. And then this pressure is released when they pass through cracks and blow out at high temperature, or sorry, at high speed, and come out as what they term cold jets. This theory isn't completely waterproof. There are some questions, including the fact of how some jets actually seem to operate before the sun actually rises in the morning, which is tricky for their model. But this is the best working model that we have at the moment. And this is a paper from their science paper, or their Nature paper describing this. So we have, we've built up an image of the polar regions where the sun never really rises. It's far above the horizon, as you see in this image. So we have a very dark area where a lot of strange sort of stuff is going on. Entered into this story the Mars Reconnaissance Orbiter. This was launched in 2005, arrived as March 2006, and had 6 months of aerobraking before it began its primary mission. At that time, the northern summer was upon us, so the polar teams got to work collecting data in the northern summer. And I'm going to just flick through some of the data that we looked at, or some of the work that we did in the first year. This is Mars Reconnaissance Orbiter in the lab, and this is the high-rise camera here. And CRISM is just a little box that's not actually visible, but it's about the size of this box here, which is probably Marcy, but it's on the other side, I think. And that gives you people for scale. CRISM has plenty of, Mars Reconnaissance Orbiter has plenty of instruments, and most are of interest in the polar regions, especially the Sherrard shallow radar, which is now starting to turn back data of what's below the polar caps. But in particular, we're interested here in this instrument, the CRISM, which is a visible to near-infrared spectrometer. This is just indicating the area of the electromagnetic spectrum that each of these instruments operates in. Yeah. CRISM operates from 0.4 to 4 microns. It's just looking at the reflected light off the surface, and it has about 512 channels available to it. The spectra commonly look like this in the infrared, so this is covering from 1 micron out to 4 microns. This is looking at a clay target. One of the goals of CRISM was to map clays at a very high resolution throughout Mars. And as a hyperspectral imager, it can look at spectra of soil and differentiate them from spectra of, say, vegetation, which is an example spectrum, and look at things like water. That's liquid water here. So these would be typical targets on Earth, not Mars necessarily. I'll show you some spectra from the Mars poles in a sec. So the data that we got to start with first was of this small crater here called Laoth crater. It has a water ice deposit in the center of it, perhaps protected by the crater. We got high-rise data and CRISM data, 2 strips here. The CRISM is this yellow outline here, and the high-rise is this red and blue line here. So we looked at these images of the water ice mound, the high-rise images, to put together a picture of how the water ice mound had actually evolved over time. Firstly, we looked at CRISM observations and determined that it also had a water ice not only around in the crater, but also on the outside part of the rim of the crater. And we mapped the depth of the absorption band of the 1.5 micron absorption band due to water, which I'll return to in a second. This gives us a first order look at the abundance of water in the water ice mound. And with work that I did with Ted Rausch, we actually did Hapke modeling of the water ice plus particulates, soil particulates. We used the Palagonite optical constants to look at the dust contamination of the water ice and how it varied across the mound. So we looked at a center of the mound and also the edge of the mound, and put together a model where we used 2 ice components and 2 dust components to model what was on the surface. This is a very highly idealized model, but it takes into account most of the variation in the spectrum. And I'm showing you here in the dots the actual spectrum, and you can see there's a little bit of noise, and the lines are our modeled spectra of the fitted spectra of the 2 points. What I've got up here in the top right-hand corner is the grain sizes of ice in blue and dust in brown here, and there are abundances by weight percent here. Well, sorry, by volume percent there. Now, what we came up with here is a very large grain size of about a quarter of the grains had to be very large in the center of the mound. So this led us to infer that all other things being equal, if the ice had been treated, hadn't been treated by, had been thermodynamically uniform across the ice, then the only effect that could be causing these grain size changes would be aging of the ice, because as ice ages, its grain size grows over time. So this led us to infer that the model of the evolution of the ice mound happened a little bit like this. The center, which had those large grain sizes here, was probably our oldest part of the ice, and we called it a mega rippled smooth cap. You can see some of these mega ripples here. This is about 35 kilometers. Oh, sorry, this is about 20 kilometers across here. Next was the dark dunes there's dark dunes that are up in the corner of the ice cap, or ice mound. And there's chaotic ripples around these dark dunes. And then the oldest part of the ice, we inferred to be the edge of the ice. So we started to build up a picture of how the ice mound may have been affected over time just by looking at the grain sizes of the inferred by spectral measurements. So there, for anyone who's interested, there is actually a paper in Icarus coming out for that data, and I have copies if you'd like to have a look at that. We're still looking at Laoth, and at the moment the North is just going through its defrosting period, and these recent images have come showing these very interesting defrosting points here on the, this is about 2 kilometers across and all within the ice mound. And you can see some of these mega ripples that I talked about. So this is within the Unit 1. So we'll be having a look at these data of Laoth, so that we're looking not just at the summer but also winter behaviour and so on. But now to move on to the guts of the talk and what I advertised in the title, so not wanting to disappoint people, we'll talk about the springtime recession in the South Pole now, which just happened last year. This is a picture that came out of a paper in 2000 of Mars mock camera results looking at the cap here at about, this is Elsebest 240, 234, 247, 260 and 267. Here you can see the evolution of the mound and the breaking off of what's called the Mountains of Mitchell here, which are actually observable by telescope from Earth. So we're going to have a look at the way a couple of different instruments have had a look at that springtime recession. But I just wanted to touch on, for those who aren't familiar with the degree of measurement of the springtime on Mars, or the year on Mars is generally by degree of solar longitude, 0 being at spring or vernal equinox, and going around to 360 here. So we have increments of 30 degrees between each of these lines here. And the period that we're interested in is the period where the South Pole is warming up over here. So this this is the spring period here, from about L sub S 180, 270, and we'll be going out to about 320 here. So this is the period that we'll be looking at here as the south is warming up. Firstly, some thermal emission spectrometer. The thermal emission spectrometer, in addition to its thermal bolometer, also carried a visible instrument that was sensitive to visible light. And this was used to put together this sequence of what actually happens over the South Pole as time goes on. This is at L sub S 150, so just before southern springtime. We're seeing a very uniform sort of cap at this time. And then at about L sub S 180, we're starting to see the beginnings of that kidney-shaped cryptic region here in lower blue, or darker colours are lower, and albedo here. And then we also get a feature of the south springtime recession, which is still lacking convincing explanation, which is a brightening of the cap as the cap starts to disappear. So you see this in these red regions, we're getting a brightening in albedo here. At the same time, the spring cap starts to shrink in, so we're seeing the CO2 ice shrinking in. At first, symmetrically around the cap, but then with growing asymmetry, especially in the L sub S 240 to 260 time period. So this sort of thing was all fairly well understood, that the CO2 was just disappearing as a function of time until the end of the summer, springtime and starting of the summer. So that was also that's how the tests started looking at the springtime recession. Onboard in 2003, the Europeans sent a spacecraft Mars Express, which had on board an instrument called Omega, which is run by a French team, and they collected data from the 2005 spring recession and reported in a great paper that came out last year by Bibbring et al. And I've taken this data from that paper. They start here, for those of you at the back who probably can't read here, this is L sub S 140 to 160. What we're looking at here is the albedo here, and the coverage is sometimes not complete. As you can see, there's gaps between the omega strips here. We're looking in the same polar stereographic view that all our images have been, with the central meridian up here. So we have the albedo here on the left. Here we have the CO2 ice band strength at 1.4 microns, and I'll show you some spectra that show you that band strength, but that pretty much tallies with the CO2 abundance on the surface. Here we have the water ice band strength at 1.5 microns, which is telling with the water ice abundance on the surface. So this is something that tests and previous instruments were not sensitive to, the presence of water ice within the seasonal cap. So this is something that Omega was able to offer, and as you'll see, CRISM is also able to offer with a little bit more. At about L sub S 180, they had almost total coverage of the area. This is 90, 80, and 70 degree latitude rings here, and 60 degree here. The cap is symmetric, and there is a little bit of water ice showing up in some regions of the cryptic region, but unfortunately, Omega has a spatial resolution at this period of about 2 kilometers per pixel, and that was limiting their ability to resolve things on the surface. At about L sub S 220 here, we're starting to see the cryptic region seeming to have more CO2 here, and a little bit more of water ice appearing around the edges of the cryptic region here. But not entirely resolved as pure water ice, but with Omega, they could only see mixtures of water ice with CO2 ice, so they inferred. L sub S 240, they're seeing the start of the asymmetry of the cap here. You also see that it doesn't necessarily tally with the albedo here. The CO2 edge of the CO2 cap is actually out here. The edge of the albedo cap is more out here at this stage here. And by LCBS 240, we're starting to see just the very last stages of water ice. Now, in the northern cap, water ice actually surrounds the entire cap as the cap recedes. So we're not seeing that. We're definitely not seeing water ice in as much abundance as the northern cap. I'll just throw that in there, even though we're not talking about the north. LCBS 240 to 249, a little bit more asymmetry of the cap and the cap shrinking in. And again, most important points is there's no water left here. We've just got CO2 ice, and the cap is asymmetrical and pretty much matching its albedo here. And then they zoom in their final couple just to the residual cap itself. So that's LCBS 320 that they end at. So now moving into the instrument of the hour, which is CRISM. Having a look at some of those polar spectra, which I promised you earlier. This is CRISM. CRISM has several different operational modes, including a full resolution mode, which has a spatial resolution on the surface of about 20 meters per pixel. And in that mode, it also takes data over 512 points of the spectrum. However, we're looking at it, in that configuration, it can only cover a square about 12 by 12 kilometers on the surface. So in that mode, it's not possible to do mapping of the surface. Instead, they have a mapping mode where they collect long strips, 12 kilometer wide strips on the surface, and you'll see these in the next images. And in this mapping mode, they just collect data in 50 spectral points from 1 to 4 microns. And that's why these spectra are a little bit coarse, shall we say. But they contain important features. As you'd expect, they designed these points to lie at important features in spectra that they expected at Mars. This CO2 ice, this is pure CO2 ice. This is pure water ice, in as much as this could possibly, in a spectral sense. And this is a mixture of CO2 and water ice, and this is dirt. You're probably saying, oh, they all look the same. They all do have very similar atmospheric features, which is due to a CO2 gaseous absorption band here at 2 microns, and also a deep water absorption at about 3 microns, which is common to everything, and water just does that if there's the smallest amount of it. But the important features that I want you to look at, and the important features for our presentation in just a second, is at 1.4 microns, I talked about Omega looking at this same area. Pure water ice, or pure CO2 ice has this sharp spike and then a little bit of a shoulder off to the side and a very high median point here, or midpoint here. Contrast that with a mixture of CO2 ice and water ice. We have this sharp spike here at 1.435, but we have this sort of lazy looking shoulder, and the midpoint never really makes it back up to the continuum here. This is an indication that there's water ice mixed in with the CO2 ice. And here you can see that pure, in a spectral sense, water ice, 1.5 micron absorption band here. So it's essentially, if you think of this plus this equals this. So we can use these to map CO2 and water ice on the surface. You'll see this dirt spectrum doesn't really have a shoulder out here. It has this 1.4 band, which is due to gaseous absorption, but no shoulder out here. So we can use these features to map over the surface. And so that's what I've been working hard on, is producing maps of CRISM mosaics. So this is starting at LCBS 191. Now I'll just explain what we're seeing here. On the left-hand side, you have an inferred ice map looking at those features which I just described to you on the previous slide. On the right-hand side, we have the 1.4 micron absorption band depth. So Where red appears on this side, we infer pure CO2 ice. Red is pure CO2 ice. Blue, and you can see some blue specks down here, is pure H2O ice, i.e. H2O ice with no CO2 ice mixed in. This cyan colour here is CO2 ice and water ice mixed in together, as I showed you before. So at LSOS 191, straight away we're struck with the difference between LSOS 191 for the Omega instrument and indeed for the TESS instrument. We have a symmetric cap as the cap starts out, it's always symmetric at about this LSOS 191. However, and you can see it's symmetric too by the CO2 amount. However, we see this huge swath of water ice has penetrated the cap and is present at this time period. Moving on to the next LSOS period, at about LSOS 199, we still see that there's plenty of the water ice present mixed in with the CO2 ice. But we're starting to see in that kidney-shaped cryptic region some areas of pure water ice appearing. So CO2 ice is disappearing, water ice is remaining in that region. And there's even, as we'll see in subsequent slides, some areas where the CO2 and water ice are completely disappearing and just leaving dirt in that region. And this is about LSOS 199. This is very early in the springtime. So it's something that hasn't been able to be resolved prior to this because we haven't had the spatial resolution on the surface to do this. In the mapping mode, I neglected to mention CRISM has a spatial resolution of 200 meters per pixel. Compare that with with Omega of about 2 kilometers at best. So that's why we're picking up more detail in this cryptic region. So as we go along, a little bit more sparse. I also mentioned that these strips are all 12 kilometres across, so unfortunately it really depends on how CRISM is operating for that these are each 2-week periods where I've merged a 2-week period of observations. It really depends on how much time CRISM is able to give to this mapping mode as to how good the coverage is. But here we can still make out some periods or some areas where there's still this water ice mixed in, but it's disappearing. You remember that it actually extended out to here at LSOS 199 or 191, so it's this water ice is starting to disappear at this time. A little bit more better coverage at about LSOS 216, and that's important because this is the time when the cryptic region is really starting to show a lot of pure water ice pixels in here. And my initial thought was, well, this is probably, and also some dirt pixels as well, and my initial thought was that this is perhaps linked to those cold jets which spew up a lot of dirt and get onto the ice. So perhaps I'm picking up some of the dust that's on the surface of the ice. That sort of seems plausible. We'll have a look at that theory in a sec. At LSOS 225, we're moving on, still seeing a little bit of water ice appearing here, but the cap is starting to be asymmetric. You'll remember at about the 220, 240 time period, the asymmetry starts to set in. Not so good coverage in that area. That was where CRISM had a cooler failure for a couple of weeks. At the other side of that cooler failure, we saw the cap is already asymmetric here, and we're almost out of water ice at about LSOS 242. And 251, there's a little bit hanging on here on the ragged edge of the polar cap. Pretty much all gone by LSOS 260. All the water ice is gone. The CO2 cap remains and continues to diminish in size as we go on, until finally it shrinks down to its residual cap size. Okay. So what is going on there? And I mentioned some of my initial thoughts on what might be happening. So now we're going to zero in on a couple of those observations, some on the edge of the cap where we were seeing a little bit of water ice around just one edge, and one in here where we were seeing some activity that I was putting down to cold jets, maybe covering up and creating some dust. Firstly, out on the edge, this crater here is called SETI crater. This observation here is what we're looking at here. We're looking at the 1 micron reflectance here, and here is an inferred ice map with the same colours as the ice maps that I was showing you just before. CO2 ice is in red, a mixture in cyan, and H2O ice in blue. So this is the edge, this is the leading edge of the observation, which is out here. SETI crater is at the end of the observation, which is here, and a little bit in the middle, just in here, is showing as blue here. This is just pure water ice, and perhaps lying in this sort of area here. So maybe associated with the crater. And so this made me think that perhaps the water ice is just being protected by the crater and the topography, the local topography. Perhaps thinking that the water ice had been a surface deposit of water ice, because as I unfortunately neglected to mention, a great issue arose when I showed this at AGU, and some of the Omega scientists came up and suggested that all the water ice that we were seeing in the LCBS 190 period was actually just a cloud of water ice over the polar cap. So that's certainly, it's certainly possible that there is some atmospheric interference. But here, we're not getting very cloud-like forms. It seems to be going, it's plausible that this could actually be a surface deposit. We'll talk in a second how we're going to resolve that in the future. Another look at SETI crater here, and we see this water ice. This was taken 2 weeks after, this observation was taken 2 weeks after the previous slide. And we're seeing some water ice here. And interestingly too, the CO2 ice remains on the other side of the water ice. So out here, there was still a little bit of CO2 ice left, and there was water ice in here and even dirt here. And we're even getting edges of the cap, a little bit like what we saw at Laoth with water being retained on the rim of the crater. We're seeing water being retained on the rim of these craters here. So a little bit of topography control. It'd be sort of very hard to call that a water ice cloud, but the jury is still not coming with its decision. So we're just looking here at this area where I thought that I was probably picking up areas of dust deposited by cold jets in the cryptic region. However, when you look at it, and this observation here is taken about LCBS 199, and the cryptic region sort of flows through this area here. This is the South Polar Cap is up here. Well, sorry, the pole is up here. And you're seeing a very broken, not uniform cap at this point. We're getting some dirt, which is brown here, some water ice in blue, and some CO2 ice in red. So we're seeing a very complex sublimation picture here. And it doesn't at all, in the visible, look like this is due to those dust caps that we were, the dust jets that we were seeing with HiRISE. Although this still could be possibly due to the fact that we don't have the spatial resolution of HiRISE, and perhaps these deposits have been homogenized at this spatial resolution. So the jury is still out, but we're certainly thinking that this could be surface ice that is just being exposed as the water, and is actually the base of the pole in this region here. You also see that in some areas, although in some areas it looks a little bit like there's clouds, these layers, or the clouds of water ice here perhaps, these blue regions here seem to be following these layers here. So it would seem that the water ice is trapped in layers at those points. So I'm thinking that the picture is probably a little bit of both, and it's not going to yield itself very easily to one solution or the other. I think water ice is probably present on the ground and in the form of clouds over this period. So how are we going to proceed with these investigations, and how are we going to separate these two solutions? CRISM has a mode called CRISM has heaps of modes, and I've only described 2 of them. This is a third, emission phase function measurements. It's mounted on a gimbal, which gives them a lot of flexibility. And during an emission phase function, as the spacecraft is flying over the surface here, it starts here, goes over here, target is here, it gimbals the instrument so that it looks forward at the target, and spacecraft flies on, gimbal turns a little, so it's still looking at the target, and it collects measurements as it's going over at varying phase functions, phase function being the angle phase angles being the angles between the sun and the observer. So this enables them to look at varying path lengths through the atmosphere. Longer path lengths here, shorter path lengths, shorter path lengths, shorter path lengths, getting longer again. So the atmospheric response should vary, while the surface response should remain the same. The observations typically take a couple of minutes, so the surface shouldn't be changing in this time. However, the atmospheric path length is varying, so perhaps we can separate out the varying part from the non-varying part. And this is the beauty of these measurements, is we can separate out the atmosphere from the surface in theory. This is how many of these type of observations have been taken in the cap. And again, this is the same polar stereographic view that we were looking at. It's just underlain by a molar image. And you can see that they're clustered around the cap, not many actually on the pole, and that's a function of the orbit of MRO. But the idea was that they'd re-image parts of the surface at different periods during the season. So they tried to do that. They weren't always hugely successful because, as I mentioned before, CRISM is also tasked with other things. Strangely enough, people are interested in areas outside the poles. I can't understand that. So it depends on how much data they're getting down from other regions. But they've done a great job to get this coverage. This is what an emission phase function actually looks like. So the ideal was just looking at one point on the surface. You'll see that actually those 11 measurements are taken as best as CRISM can do on the surface, but at one point. But unfortunately, when they go through all the computations and work out where those points actually laid, in here you'll see there's a distribution of roughly 1, 2, 3 areas over the cap for the entry, the over the top, and the exit of the observations. So they're not quite taking the surface. And that's something that we need, the same surface point. So that's an idealization, but if we can believe that, and these are 12 kilometers across here, roughly 12 kilometers across. So if we can believe that the surface is homogeneous on a roughly 10 to 20 kilometer scale, well then we can go ahead with our emission phase function measurements. And here we've started to look at what they actually look like, and this is pulled from my LPSC abstract. And of course, there's still a little bit of work that needs to be done here. The red measurements, or the red points, are actual measurements. The blue measurements, or the blue points, are just if the surface was an isotropic scatter and was obeying the Lommel-Seliger law, which is highly unlikely for water ice, but more likely perhaps for a dark, flat surface that the light just scatters straight off. I won't go too much into those details, but you'll see that importantly, it fails to reproduce the surface, or fails to reproduce the response of the emission phase functions. And this is an actual emission phase function measurement. These points come from each of those segments. So there should be 11 here, 5 here on the outgoing. Sorry, that's 5 in the incoming. This is 1 in the center, 5 on the outgoing. And they actually take an image of 24 points, so that's why we're seeing some spread here. Now, an EPF is also done for each full resolution targeted observation. However, the main point of me showing this is that these are really much better than the actual EPF measurements because they take data right along this area here. You'll see the previous one had just one data point here for a phase angle of about 52 degrees, and this one has coverage over the entire image, which is a lot better for trying to fit it with data, but you'll see our model fails miserably here. So we have plenty of work to do, and we expect that things will improve once we start putting in an absorbing atmosphere, and absorbing and scattering atmosphere, and gaseous absorption as well. So this is just the beginning, and I'd like to thank you for your attention and ask if there are any questions. Bob, yeah.
I was really struck by the distribution of water in the seasonal cap and also this 190 or so, being so confined to one hemisphere. One way to potentially distinguish that water from clouds versus being incorporated in the seasonal cap is the time at which it disappears. Because I would think that any water that disappears and exposes the CO2 underneath it must be in the atmosphere. Because water that's incorporated in the cap wouldn't be released until after the CO2
disappears. Yep. Yep. No, it's an excellent suggestion. I hadn't thought of that, so I will go back and armed with that piece of.
I'll also mention that our group is doing a lot of modeling of water cycle, and certainly be very interested in working with you on that.
Absolutely. I hope so. I hope we can do that.
You mentioned it earlier in your topic. I was kind of waiting for you to come back, but you didn't. You mentioned the spiders.
Yes.
Is there any correlation with certain areas, like the CO2 water ice area or the CO2, with where they're formed? Have you noticed any, or have you got?
It's certainly. I introduced the spiders only to talk about them as a possible reason for why I was seeing dirt appearing very early in the spring. And at the spatial resolution of the maps, I'm finding it difficult to resolve individual spiders at 200 meters per pixel there. As you'd expect, since we didn't see them until we had mock images of the South Pole. So the correlation between the spiders and where I'm seeing the dust is still an open question, but I was surprised that it didn't pop out more. And in that image that I showed, it seems to be a large area that's covered by that has no ice on it, and it doesn't seem to be associated with any spider features that I can see or that are clustered nearby, going by Tim Titus's maps of spider features. So at the moment, I haven't found a correlation between them, but I'm certainly looking for it.
And I know Candy Hansen's been really retargeting some spider locations.
Yes.
Maybe that we might want to collaborate with her on some of those areas.
Absolutely.
The other point that I was kind of interested in, some of those spiders actually have channel-like features radiating from them.
Right. Yeah. Yeah. I saw Candy's talk at AGU, a great talk, and she showed that there seemed to be an underground network linking these spiders that was resolvable with high-rise images, and so she was suggesting that the whole network was pressurized, and in fact, we don't necessarily see spiders reoccurring at the nodes of these networks, but they can occur anywhere off these networks, which is a very interesting sort of observation, suggesting that they're all interconnected and they could shoot up at any time. They're not all necessarily going to cluster around one point. Yeah, but I think that those observations are just beginning to, but they're making great progress with high-rise. Josh.
I forget the name of the crater that you talked about at the beginning, I think near the North Pole.
Yeah,
And you said that
Laoth.
there were mega ripples in the ice mound. Are those ripples in the ice, or are they the underlying material?
Let me go back. Yes, it's a good question as to what. Oh, this is going to take me a while to go back. Let me. It's a good question as to how the underlying topography matches up with the what we see. There are definitely ripples here, and you can see them just at this. This is a CTX image actually underlaying this map, and as to how much they're controlled by the underlying topography is a good question. But there aren't any ripples outside the cap, so it's and this is I have been thinking that these are related to the wind direction when the cap has been modified. And there are, in fact, smaller ripples that you can't see in CTX images, but you can see in high rise, which we put images of in our paper if you're interested, that seem to be pointing towards these mounds. And they're even harder to explain because they appear to be icy at the base, but then have a dark edge to the top, which I find extremely hard to explain. But it's definitely not a shadow effect that we're seeing, but it's a dark top. So for any other polar investigators who find these features, you might want to also look at this crater for analogous features. And they also have a ripple to them, so they sort of look like they're snaking along the ground. It's a pity I didn't have that image, but you can catch me for a copy of the paper if you like.
Does that ice survive all summer long?
This ice does. This is a perennial water ice deposit in the north. And the reason that we chose to look at it is exactly that reason, is that it's the southernmost large water ice deposit. It's at 70 degrees north, so it's 30 degrees off the pole. And there are smaller water ice deposits that are lower, but they're just flex. They're meter scale deposits. This is again 20 kilometers across, so the largest big one.
Adrian, there are features in a crater about at that latitude, a little bit south of that are thought to be pingos. And pingos require liquid water at some point in the past or in the seasonal cycle.
Yeah.
But you're not really, I don't know how you would see any evidence for the phase change in water there, but do you see anything like that? Do you see any rivulets or channels?
We haven't actually. We haven't seen any channeling. There's no anastomizing features that seem to be due to liquid water. It all seems to be aeolian and condensation sublimation, explainable by aeolian or condensation sublimation regimes. And we don't see anything that I'd describe as a pingo. Interestingly, just outside the ice mound in this region here, it's not resolvable here, but there are massive polygonal cracks in the base of the crater. And the cracking is very large in scale, close to the ice mound, but then dies off out from the edge. So by the time you've got a couple of kilometers from the mound, there isn't any more polygonal cracking. And also, there are flecks of ice around the edge here, which make us, in the paper we suggested that the water ice is retreating at the moment because of those water ice specks around the cap, or around the mound. But this was really just a first look at summer details, so at looking at this mound in summer. So it'll probably be very interesting to go back to. And as an isolated deposit, it's a bit like throwing away other more complex processes that are going on and just looking at what actually would affect an ice mound at this latitude. And it's a good it's a good thing to test models against.
All right, well, let's thank Adrian again.